Okay, and a controlled data flow graph model, in that state machine model is the one of the best example. See here, state machine model is used for generally modeling that synchronous sequential circuits. Synchronous sequential circuits. Basically, this modeling is a reactive or event-driven embedded system. Okay, and based upon the actions, uh, state transitions occurs. Okay, that's why here all the votes, especially for the state machine model, is represented with state, event, actions, transitions. Okay, these are the key terms. Okay. The state machine model is especially used for modeling and reactive or event driven embedded systems whose processing behaviors are independent on state transitions. Of course, it is the synchronous sequential circuit design. Okay, synchronous sequential circuit design methodology always involves present state output and next state input. Okay, and just like what is the difference between these two? Combinational and sequential. In combinational, output always depends upon the present combination of inputs, whereas in sequential, output depends upon the not only present input but also previous outputs or previous inputs. Why? Because there exists some feedback. That's why the state machine model is always the event driven model. Okay, this state machine model is just utilized here for the design of an embedded system. Okay, where the processing behaviors are dependent on state transitions. Here, embedded systems are used in control and industrial applications. So, a typical example here considered as a, okay, here consider one example. Okay, there is a fire alarm. Okay, here the state machine model describes the system behavior with states and what is the present position, present state, and events, actions, and transitions. Okay, the state is representation of the current situation. Okay, at what position is in, okay, holding. Similarly, an event is an input to the state. An event, okay, event is always the input to the state. Okay, event, that event especially acts as a some stimulus for state transition. What is meant by stimulus here? And upon what condition? Okay, the state move from one state to another state. Okay, and one state to zero state, or zero state to zero one state. Okay, okay, on what basis it is moved from one state to another state? Okay, that is the event. The event acts as a stimuli for state transition. Okay, and transition is the movement from one state to another state. Okay, here state is the position. Okay, the event acts as a stimuli, and transition means moving from one state to another state, and action is an activity to be performed by the state machine. And what type of uh, uh, activity? Okay, what type of action? Okay, it is performed, is considered as an action of that state machine. Okay, and generally that's all about the machine model. Okay, see here, a finite state machine, the name itself indicates it is having, of course it's the state machine, but there exists only a finite number of states. That's why that is called a finite state machine model. Okay, A finite state machine model is one in which the number of states are always finite. That's that is called a finite state machine. In other words, the system is described using the finite number of possible states 0, 0, 0, 1, 1, 0, and 1, 1. Okay, it is always bounded. Okay, that's why that is called a finite state machine. Okay, here they consider an example. Okay, observe here. As an example, let us consider the design of an embedded system for driver or passenger seat belt warning. Okay, here they consider, of course, you can take any example. Okay, just like a fire alarm. Okay, or simply agriculture related applications as a soil testing, whatever it may be. Here they consider uh, one example as a seat belt warning. Okay, and when you not wear the seat belt, okay, while you are sitting in the car, okay, obviously it indicates some buzzer indicates with buzzer sound or some blinking, light blinking, right? Okay, that is called seat belt warning in an automotive automotive and automobile applications, okay, in cars using FSM model. The system requirements are captured as, okay, remember here we are going to design an state machine model. Okay, here we are going to design one state machine model. Okay, the problem statement here is seat belt warning. Problem statement here is seat belt warning. Okay, and when you know aware seat belt, obviously it indicates with either buzzer or some light blinking. Okay, some red light blinking. Okay, that is the seat belt warning. Okay, in cars. Okay, the system requirements are captured as, and to design that state machine model for the purpose of the seat belt warning implementation, state machine model implementation. See here, what is the first requirement? When the vehicle ignition is turned on, and when I started the car, okay, when I started the car, on seat belt is not fastened within 10 seconds of ignition on, the system generates an alarm signal for 5 seconds. Okay, okay. And I just when we enter the car, okay, just I started that car. Okay, after starting the car, within 10 seconds, it detects is it you wear that seat belt or not. Okay, for suppose you not wear any seat belt, okay, obviously it generates an alarm signal, okay, for few seconds. Okay, here they mentioned to 5 seconds. Okay, here we are going to design one state machine model. Okay, identify these requirements. When the vehicle ignition is turned on and the seat belt is not weared within 10 seconds. First hand means weared. Okay, 10 seconds. Okay, then the system generates alarm signal for 5 seconds. Okay, ignition system on within 10 seconds of ignition, and if not wear any seat belt, okay, within 10 seconds of that identification, it automatically generates 5 seconds length alarm signal. Okay, these are the requirements you have to observe. See here, that is the first requirement. And second requirement, the alarm is turned off when the alarm time 5 seconds expires. Okay, and what they told exactly here, if you not wear seat belt within 10 seconds, it obviously generates an alarm signal with a duration of 5 seconds. Okay, after the 5 seconds, if the 5 seconds is expired, okay, or if the driver or passenger fastens the belt, or if the ignition switch is turned off, okay, whichever happens first. And for suppose that duration is over, is the one condition, and second condition is, okay, if the driver turns off that engine, okay, ignition, and the car is halted and engine is completely off. Okay, and that is the second situation. Okay, the alarm is turned off and the alarm time expires, or driver fastens the belt. Okay, the driver or passenger fastens the belt, and if for suppose he wear the belt, that is the another. If the ignition switch is turned off, and possibilities to turn off that alarm is first one is if the duration time is expired, and second one is, okay, if the passenger or driver wear the belt, and third one is maybe the ignition is off. All possibilities, just you have to check for the all possibilities. Okay, here listen carefully. Here states are alarm off, waiting, alarm on, and the events are ignition key on, and when we enter the car and when the car is started. Okay, and ignition key off, time expire. These are the events. Alarm on and off and waiting is the states. Okay, alarm time expires, seat belt on. Okay, okay, these are all events. Okay, here the states are alarm on and off. Okay, in between some waiting. The events may be ignition on and off, or maybe time expire, or for suppose he wears the seat belt. Okay, or alarm time expires. Okay, and these are the points observed from this. Okay, two statements. When the vehicle ignition is turned on, okay, the seat belt is not fastened within 10 seconds, and alarm signal is for 5 seconds. Okay, and second case, alarm turned off when the alarm time expires. Driver or passenger wears the belt. Okay, if the ignition switch is turned off. Okay, consolidate from these two and separates what are the states and what are the events. Okay, here the states are maybe alarm on or off. Okay, and events may be, okay, car on, car engine on and off. Okay, at the two situations, okay, there is a possibility of alarm on and off. Time expires, it is going to alarm off. Alarm time expire and seat belt on. Timer expire and alarm time expire. Okay, and wear the seat belt is the one possibility. For suppose he wears maybe ignition is off. Okay, that is another possibility. Understand? Okay, the same is represented with diagram here. Okay, the same is represented with diagram. See here. See here. Alarm on, alarm off, and waiting. Three states. Okay, alarm on, alarm off, and waiting. These are the three states. Okay, but when the alarm is going to on and when the alarm is going to off, okay, what are the possible states? Those are called events. Those are called events. See here, when ignition key is just when we enter the car. Okay, initially alarm is in off state. Okay, when your car door is open and just you enter into the car seat, and simply the ignition key is on, okay, and car is started. Okay, after few seconds, it checks for is it the car belt is the, okay, you wearing car belt or not. Just it checks for you wearing car belt or not. Okay, that's why that is called waiting. Okay, for suppose you not wear any seat belt, that's why that alarm is on. Okay, that is the meaning of timer expire means it's checking for, okay, you wear car belt or not. Did you wear car belt or not? If not, and that is the timer expire, that is alarm is on. But when that alarm is going to off, when alarm time expires, that alarm time is generally here, especially in problem statement. Okay, it is on period for 5 seconds. Okay, after the 5 seconds, it is going to be off. That is the one possibility, and second possibility maybe seat belt. Okay, okay. Meanwhile, you wear a seat belt. That is the second possibility. Seat belt on. Maybe the person turns off that engine. Okay, that's why there is ignition key off. Okay, so uh, okay, those are the possibilities of okay of this alarm. Okay, alarm time expired, seat belt on, ignition key off. Okay, that's why it is going to alarm off. Again, ignition key on. It is stating still in waiting state. Or suppose ignition key off again it is going to alarm off. Okay, or a seat belt on. Okay, did you get it? This is called state machine. Okay, this is called state model diagram. See here. Okay, that is the explanation. Okay, the ignition key is on. The event triggers 10 seconds timer and transitions the state to waiting. Okay, if your seat belt on or ignition key off, event occurs during that wait state. Okay, the same diagram is explained again here. Okay, the state transitions into alarm off. Okay, when the wait timer expires in the waiting state, the event timer expire is generated. It transitions state to again alarm on from the waiting state. Okay, the same diagram is explained here. The alarm on state condition continues until your seat belt on. Okay. Okay. Again, the occurrence of any of these events, the state to alarm off. Okay, all are the possibilities. Okay, the wait state is implemented using a timer. Already, you know, the timer also has a certain set of states and events for state transitions. Okay, using the FSM model, the timer can be modeled as shown in figure. See here. Okay, figure 7.4 is okay, the next one. Okay, timer modeling is shown in next figure. This is the timer, FSM model for timer. Okay, okay, and how could you generate the timing signals from that microprocessor or microcontroller? Okay, whatever the clock generated by that oscillator available in that microprocessor or microcontroller, from that we are implementing timer. Okay, timer signals are inbuilt already. They are having some timers. Timer one, timer zero, timer one. Just like in 8051, it is having two timers as a timer zero, timer one. Okay. See here, this is the implementation of the timer. Okay, this is the ideal state. Okay, initially that is always in the ideal state. If the event occurs, then it loads the timer. Okay, if the event occurs, whatever the ignition is on, okay, that is load the timer. Okay, and action, what action it is, it has to be performed. Timer count starts. Okay, the timer count is the one variable that is assigned with a new count. New count of how much here? After ignition starts, after the ignition starts, in what time? Okay, uh, in what time the alarm is going to on? How much time is given in the problem statement? 10 seconds. Okay. Okay, and here the event is the load timer action. What action it is performed? The timer count is the variable that is assigned with a new count. That new count is a 10 seconds. Okay, that's why that is going to idle state to ready state. Okay, when it is loaded with the 10 seconds, when ignition starts, okay, the timer is going to on. Okay, start a timer. Okay, start timer is the event occurred and what actions is performed. Okay, some countdown is started. Okay, 10 seconds to 10, 9, 7. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, after the 10 seconds is expired, okay, event, it is stop timer or timer expire or action set a timeout flag and our timeout interrupt. Okay, again goes to ideal state. Okay, that is the FSM model for timer. Did you get it? Okay, that 10 seconds or 5 seconds. Okay, how it knows? Okay, just this is the machine. Okay, just this is the machine, but how it knows or how it understands these timing signals. Okay, how it knows that 10 seconds or 5 seconds. Okay, all this because of, okay, the FSM model implementation of the timer. Get it? These are the timer states: ideal state, ready state, and running state. And these are the events and actions, and what actions they have to be performed and what event, okay, occurred, okay, while transition takes place from one state to another state. See here. Okay, this is the part. As seen from that FSM, the timer state can be either ideal or ready or running. During the normal condition, when the timer is not running, it is said to be in ideal state. That is by default. And when there is no machine starts, I mean, no engine starts. Okay, the timer is said to be in ready state when the timer is loaded with a count. How much count here? Especially, okay, our problem statement. Okay, it is going to be ready within 10 seconds. Okay, the timer is set to be in ready state and the timer is loaded with a count. The count is 10 seconds corresponding to the required time. That is the required time is the 10 seconds, right? Okay, the timer remains in the ready state until the start timer event occurs. Okay, the timer changes its state to running. Okay, the timer changes its state to running from ready state on receiving a start timer event and remains in the running state until the timer count expires or stop timer event occurs. Okay, the timer state changes to ideal from running on receiving stop timer or timer expire event. Okay, that is all. Okay, easily understand from the diagram. Okay, see here. This is the one case study or simply problem. Design a automatic tea or coffee vending machine based on FSM model for the following requirements. Okay, see here. This is not a new topic. Okay, uh, this is these are the last concepts in, okay, digital circuit design. See here, the tea or coffee vending is initiated by user inserting a 5 rupee coin. After inserting the coin, the user can either select coffee or tea or press cancel to cancel the order and take back the coin. Okay, and how to deal with such FSM or state machine models is, okay, you must be in conscious and followed step by step. Why? Because that is the machine, they don't know anything. Okay, what they have to do, what actions they have to be performed. Okay, what transitions they have to take. Okay, all these are you have to mention. Okay, uh, and how, okay, how best you have that micro thinking. Okay, okay, that how best you are, okay, in designing that state machine models. See here, a tea or coffee vending machine is initiated by the user inserting a 5 rupee coin, and just I am inserting 5 rupee coin and select tea or coffee. Okay, that is the they try to tell us after inserting the coin, user can either select coffee or tea, or simply press cancel to cancel the order and take back the coin. Okay, and when I press the cancel, simply they that machine throw back that 5 rupee coin. Okay, the FSM representation for the above requirements, okay, given in this version. Okay, the same is implemented here. See, okay. The by default state A is the wait for a coin, and just like a weighing machine. Of course, the weighing machine doesn't contain okay these many states. Just to have insert 1 rupee or 2 rupees coin. Okay, simply that dispense. Okay, that card with our weight. Okay, here also the same. Initially, that is always in the wait for a coin. Okay, state B, wait for a user input. Just I am inserting the coin. It's step one. Next, you have to choose is it okay, and if you want either tea or coffee. Okay, that is the user input, or simply you okay you press the cancel button. Okay, next, for suppose you select tea. Okay, if you select tea, if you select tea, simply uh, it fill out the glass with tea. Okay, or simply if we select coffee, simply it dispense coffee. Okay, these are the states. See here, state A, state B, state C, and state D. For suppose state A, if I insert a coin, if I insert a coin, okay, it asks us about okay what is your choice. Okay, event insert a coin action. Okay, okay. For suppose if you insert a coin and cancel, simply cancel. You press a cancel button. Then the coin is simply throw out. Okay, these are the states. Did you get it? State A to state B. Okay, if you insert a coin and okay, then it asks about is it you want tea or coffee. For suppose you insert a coin and press the cancel button, simply throw out the coin. Okay, that is state A to state B transition. Okay, the state B. Okay, for suppose uh, you wanted tea or coffee. Okay, for suppose after insert a coin, you okay, okay you wanna drink a tea. Okay, just you have to press a T button. Okay, then it's going to state C. What is the state C here? Simply state C is the dispensing tea, okay, into that glass, okay, or paper cup. Okay. Or for suppose if you want a coffee, again it goes to state D. Why? Because here tea or coffee, two choices are there. Okay, of course three choices: tea or coffee or cancel. Okay, I don't want to know anything. Action dispense a coffee. For suppose it dispenses tea. Tea is dispensed. Okay, the tea is dispensed. And if the action uh, covered, okay, again it goes to state A for another user input. Okay, for suppose here the coffee is dispensed. That's why again it is go for initial state and wait for a coin after the dispensing. Okay, get it? Right? Did you get it? Okay, do you understand the example? Coffee vending machine. Okay, the same is explained here. Okay, nothing in that theory. Okay, initially it is in the waiting state, wait for a coin. When the wait for user input, dispense tea and dispense coffee. The event insert a coin and a 5 rupees coin. The transition state to wait for user input, and from wait for user input to uh, that second state, that is insert a coin. The system stays in that state until user input is received from that buttons. For suppose when I am pressing the cancel or tea or coffee, okay, if the event triggered in a wait state is a cancel button press, the coin is pushed out the state. Okay, again wait for a coin. If the event received that wait state is either tea or coffee, then state changes to dispense tea. The dispense tea or dispense coffee. Okay, once the coffee or tea uh, vending is over, again it goes to user input. Okay, wait for a coin state or again for okay, and a default mode. Okay. The few modifications like adding timeout for the wait state, okay, wait state. Okay. And currently the wait state is a infinite. Okay, it can be redesigned to timeout based wait state. And a timeout means even in the ATMs also you observe that a timeout. Okay, if no user input is received within the timeout period, the coin is returned back and the state automatically transitions to wait for a coin on the timeout and capturing another events like water not available, tea or coffee mix is not available. These are the additional features. Okay, and changing the state to an error state. Okay, these are all observed in the ATM machines, right? Can be enhanced to add this design. Okay, it is left to the readers and exercise. Okay. Did you get it? Okay, did you understand? Okay, that's all about state machine modeling. Okay, remaining all are, this is quite different. This is not belongs to our syllabus. Okay, that's all about final state machine model and that state machine implementation. Okay, that's all about today's class. I will continue in the next class. Okay, thank you.